Okay, we'll go ahead and get started. I'd like to welcome everyone and thank you for attending. I know it's right before the holiday season. That always sometimes can be a difficult time to attend these things. My name is Rick Dye. I'm the Key Account Manager for Flow Meter Products for Teledyne Isco. Today we're going to talk about latest on laser. This is a series of 4 we've done in 2016. And really the reason we're doing this is to both educate everyone on the technology, but as well as discuss some of the other older technologies. But the laser continues to just amaze anyone that uses it in some of the applications where it will work where other products won't. So that's why we call it latest on laser. Today what we're going to do is we're going to review some of the area velocity measurement techniques and technologies that are currently on the market today. We're going to discuss fairly detailed the laser flow measurement theory and operation. And then we're going to look at some applications where the lasers work where other technologies just will not work. Equipment options, we're going to talk about a couple different types. One will be the signature on the bottom left. The one in the upper right is the 2160, which is our flow logger. The differences between those, one is a permanent flow meter, which again is a signature, has a smart technology capability so you can connect multiple sensors to it. The one on the upper right is more of a field rugged unit, is submersible, designed to be in the manhole where the environment is very nasty. One thing that we always try to do with not only ISCO technical support people, sales people, and our local sales reps, we want to make sure we provide the right product for your application. So we always review those. Typically not one product is going to work in every location, so we want to review your application, make sure we get you what you need to do, the job you need to do. The ISCO Flow Lab, this is, again, our facility here at Lincoln, Nebraska. This is an incredible facility, and we do a lot of training there. We also do design development. We can tell you how wonderfully accurate everything is, but it really is a great development tool for us, and I think that's one thing that gives us a huge advantage over even our competition. So let's talk about area velocity flow measurement. Some of this will be reviewed for those of you that have attended in the past, but it doesn't hurt to probably go through it again. So area velocity, Q is your flow, is equal to the area of the water, which is normally done using a level measurement technique. Could be either pressure sensor or an ultrasonic sensor. Velocity is your V component. That's normally done these days using a Doppler principle. Today we're going to talk about a couple different types that Teledyne Isco has. One is what we call contact, and that can be one of the older 2150 sensors or even the newer 350 area velocity sensor that is a smart sensor. We're also obviously going to talk about non-contact, and I'm talking about laser in this case. So our Doppler velocity measurement, basically a sensor on a ring. It's in a pipe. We need to measure our level. We do that using a pressure sensor. We transmit out the nose using a continuous wave Doppler sensor. What we get back is something that looks very much like this. You don't see that from the naked eye, but if you look into the software, you can see some of this stuff. But basically, this is the frequency shift of what we're getting back from a continuous wave sensor. What we do is we trim off the front end, back end of that signal, and we do a weighted average of what remains. This has been a very good method for measuring water velocity and flow in a channel, but they do have some limitations, and I'll talk about that in a minute. The 2150 was designed to be a modular system, so you could stack up to 4 modules. So if you had an application where you needed multiple sensors in one manhole, you could just stack up to, again, 4 AV sensors or modules to do that. All of our meters are battery powered, can be battery or AC powered. We do not require you to buy our proprietary batteries. These are all off the shelf, either alkaline lantern batteries or even deep cycle batteries. One thing to note that not all batteries are created equal, so that's one thing you want to keep in mind when you do get into a flow monitoring program. This just is one example of 2 batteries that really cost about the same, but the weight really tells you the whole story there. The Energizer is significantly more powerful than, in this case, the Duracell Pro Cell. So just keep that in mind when you're doing any monitoring. So continuous wave Doppler, some of the advantages, they work very well in depths typically lower than 24 inches. The signal of a continuous wave sensor will get scattered as it gets further away from the sensor itself. So as you get deeper and deeper flow, your accuracy will decline. And that's true with Isco, that's true with anybody else's continuous wave Doppler sensor. So for that reason, we know we're going to be in the 5 to 10% range when we have depths typically lower than about 24 inches. Because we're shooting a shotgun pattern out, we do a good approximation of the velocity of the water. These are low power consumption units. They can be both portable or permanent, and they're going to be typically lower cost. Disadvantages of something like this: you have a sensor that's in the water, you have debris issue potential, ragging, damage to a sensor in a case of maybe stormwater or a CSO. Periodically, you'll have to calibrate those sensors. We use, again, a shotgun pattern. It does a great job of giving you a good fluid velocity, but it does have limitations when you get above 24 inches. Having said that, that does not mean you cannot use an AV 2150 or a 350 in a big pipe. People do it all the time, but it just means that you need to be aware that your accuracy will not be great when you get in a 10-foot pipe and you're 7 feet deep. So you understand that. Again, for that reason, they're better for smaller pipes. Okay, so that's the continuous wave sensor technology. I'm going to talk now about acoustic Doppler flow meter, or the ADFM. Some of you are probably familiar with this thing. It's been around for quite a while. What it does is it has a sensor that has 4 different crystals on the top. 4 of them are used to measure the water velocity. The one in the center is used to measure the water depth. If you look at this, this is a theoretical velocity profile. In this case, the levels being measured right in the middle, using an upper-looking ultrasonic. We are able to dissect the flow into multiple bin velocities in order to get a velocity distribution or velocity profile. These are probably one of the most accurate technologies that we know of in open channel. This unit now will be eventually phased out and replaced with this technology, which is called the AccuPulse. What the AccuPulse is a 3-sensor design as opposed to the 4. It uses a frontward-looking velocity sensor, transmits up through the water column, and dissects the flow into 9 different velocity bins in a shallow water mode. When the water exceeds 30 inches, it will go into what's called a deep water mode, and it can do a much more in-depth velocity profile. What you get back from this, and why these are very popular, is you can see here we have a couple things. One, we have diagnostics related to what's called signal strength, so we can tell if any of the crystals are being obstructed. We have another one called correlation, which is similar to a 2150 spectrum. How much of that data we think is real and what do we like about it. Finally, we have what are called velocity bins. In the case of the AccuPulse, we need 9 velocity points, or 6 out of 9 to consider it a valid reading. This particular reading right here, we had all 9, so we know that it was a good reading. And to the left of that, you can see the velocity profile. So the acoustic Doppler flow meters do a complete velocity profile, which is pretty incredible. So some of the advantages and disadvantages of pulse Doppler. You're going to need about 5 inches minimum on the large pipe one. The AccuMin, which is a smaller, or it's AccuPulse with a small sensor, can read down as low as 3 inches. These are flow accurate to 2%, which is the best in the industry for open channel. They do a complete velocity profile using discrete velocity measurements. Nothing else does that. They can read up to 20 foot of depth, both portable or permanent. Use a non-drifting ultrasonic level sensor. No calibration is required. Once you set that thing up, you're pretty well done. Some disadvantages. You have to have the sensor in the bottom of the channel. And when you do that, you have the obvious challenges: debris, ragging, potential damage to a sensor, and you're going to need a little more water flow. So you need at least 5 inches and preferably more than that. They're going to cost a little bit more than a standard continuous wave Doppler. They're going to use more power. And installing these in some of the large pipes that we see these days can be very challenging. All right, so that is Isco's contact sensor technology. What we're going to talk about now is non-contact. Why would you want to do non-contact? Non-contact, obviously safety is a big issue. You don't want to be in that manhole any more than you have to. Maintenance is also a potential issue. This is, nothing's going to work if it's covered in this kind of debris. Okay, so what Teledyne did is we developed a product that we feel will really unlock the door to successful monitoring program, and that is called the LaserFlow. The LaserFlow uses a non-contact laser velocity sensor, uses a non-contact ultrasonic level measurement technique, and then when it does become submerged, it uses a continuous wave Doppler sensor to read the surcharge. So, theory of operation behind this, there is an ultrasonic sensor in the upper right back that is at a slight angle. It transmits off a 22.5-degree deflector, knows where the water is. Once it knows where the water is, it focuses the laser beam below the surface of the water. This is very key and unique to Isco and the laser. This is also a very patented feature. So nobody can read subsurface velocity measurement with the exception of LaserFlow. Before I get into the laser operation, I'm going to talk a little bit about the ultrasonic. One thing we looked at when we designed this was what the other guys did well and maybe areas that we can improve on our design. So one of the things was the ultrasonic sensor. If you have an ultrasonic sensor that's mounted looking straight down, you can have the potential for condensation to drip off the nose or the face of that sensor. What we did with the LaserFlow is we angled it, put it in the back of the sensor, and now any moisture that accumulates will just run right off it, whether it's moisture in the manhole or becoming submerged. We use, again, that deflector plate. One of the reasons we do that is any ultrasonic sensor will have a deadband, including us, and that's normally about a 12-inch deadband. With the design, we've eliminated that deadband because now it's taken into account in the sensor position. We can read all the way up to when the laser goes underwater before it will hit the deadband of the ultrasonic sensor. We have a 0 to 10 foot range, so the thing can be 10 foot above the minimum depth of water flow. So we did, I think, a really good job on the ultrasonic. Very rarely do you have to do anything with it. So water level comes up, submerges it, goes back down. It should kick right in and start working. Okay. So that's the ultrasonic. The laser, how the laser works is kind of like if you took a magnifying glass and you moved it until you got a small point on your hand where it started to burn. Very similar to what the laser does. We know where the water is and we focus the laser at the appropriate point. Any signal reflected off the laser will be looked at basically, but most of it will be weak and really not even processed. So anything on the laser beam will be reflected. What we are interested in is the focal point, where we are actually focusing the lasers, where we get our maximum signal reflection back to the laser sensor. It works like any other Doppler device. We transmit a known frequency, we know the frequency shift of what comes back, and that's how we calculate the speed of the water. So, give you a better idea, front view, side view, we do a level measurement, we know where the water is, we focus the laser below the surface of the water. Where we focus that laser is known as the converging section or point of convergence. What's unique about the laser is when we take that reading, we take 5,000 velocity scans in 2 seconds. So it does a very detailed analysis of what it's getting back in a very, very short amount of time. For those of you that may be aware of Laser version 1, which was released about 4 years ago, that signal took about 45 seconds to process. We did some changes in the firmware and some other things. Some of the engineers did a great job. And now it does a lot in a much shorter time. So incredible what the laser does. This is a velocity spectrum. This is similar to what I was showing with the 2150. The laser does something similar to this. So every scan of the laser, the frequency on the bottom, 0, and then to the right is your higher speed velocity. What this tells you is everyone that agree on the speed of the water or that frequency shift, the more area under the curve or the more of a Doppler signal we will see. This is stored as a diagnostic value in the meter, so we can tell very confidently if we're getting a good reading or we're not. We slice off front end, back end, and we end up with something like this. This is a new laser. If you got one today, it would look, your signal look like this. What's key about this is our Doppler power, which is really a measure of signal to noise ratio, is incredible. as this water slows down, that peak you see would shift to the left. The first version laser would not read below about 0.8 feet per second. The current lasers now are spec'd to a ½ foot per second, but in this case, we can read much lower than even a ½ foot per second. Again, measurement of the quality of the reading. This value, Doppler power, is stored as like a data point, just like a level or velocity. We need to see a value greater than 1,000 in order to consider it a valid reading. So with any other Isco flow meter, we are really, really big into diagnostic. We not only want to give you a nice, pretty graph and a good-looking set of data, we want to verify and we want to be confident that the reading you're getting is truly a valid reading, and the laser is consistent with that. Okay. So this is one of the diagnostic files that we get from a meter. A couple things we do. One is the laser has a built-in accelerometer. It knows its X, Y axis, so it knows if it's level. The X is supposed to be 0 plus or minus 3. Y is 45 plus or minus 3. So we know in this case we're getting our sensor has not shifted. In the case if it did go submerge, went underwater, water level comes back down. When I look at this diagnostic, I can see that I have no changes in my position of my sensor, and I also note I have a good velocity Doppler shift, so no reason to touch that laser. Just leave it alone. Okay, so how do we run this thing? It can be ran at multiple different ways, but one common way is what's called single point velocity method. We read a ultrasonic level. We know where the water is. Once we know where the water is, we focus below the surface of the water. At that point, we're taking 5,000 velocity reading at that point. The other way is we can take and measure multiple points. The laser can read up to 15 different points. It can read 5 points horizontal, 3 points vertical. Don't want to mislead anybody. This does not do a complete velocity profile like an ADFM. So if you have very irregular hydraulics and the bottom's moving one direction and the top 5 feet's moving the other, the laser will not see that. So it's not going to read every application. But for the most part, in a normal hydraulic condition, your peak velocity is typically in the middle, just below the surface, and then as you get to the outer walls, it will slow down. This method, though, is known as a multi-point, multi-depth velocity method. So here's a site that I downloaded actually in Washington, Seattle last week at an application. It was a water coming into a wastewater treatment plant. I turned on all 15 points, and you'll notice that the upper left, so it starts upper left, moves across to the right, 5.03 feet per second, and 4.71 to the right. Very uniform flow, so everything looks good there. The choice for them is really power. You can run all 15 points. You know, if you have AC power, then run them all. It doesn't matter. In this case, they did, so we just left them all on. Billing applications, you may want to run all 15 points. If I have them on batteries, I may not want all 15, especially when it's as uniform a flow as this is. You may want to pick 2 or 3 different ones. It's important to note that if you select 2 or 3, if they do ever come up invalid, which means that they didn't like what they saw, they will not be processed and used for the velocity. It'll just be thrown out. Here's the site that was an influent of a wastewater plant, actually in Hawaii. You'll notice the upper left was showing 2.49 feet per second. The point in the middle, 4.98 and 5.37 to the right. This was a very irregular velocity profile. In this case, we'll average all of those values and calculate the speed of the water. So challenging. But if you had to do this, a laser is really the only thing that will give you this kind of detail. Okay, so that's the laser operation. Now we're going to talk about what we do when we go underwater. In this case, this was a sanitary sewer overflow. It happened because pumps at the wastewater plant shut off. The laser was under about 15 foot of water. It is rated 6 feet, 72 hours. We have lasers now. We don't recommend putting them under 15 feet of water, but we do have lasers that far exceed the rating and have not leaked, so it's a very, very durable product. So what we do is, once the laser becomes submerged, we have a continuous wave sensor like a 2150 or the 350 area velocity sensor. It is mounted upside down on the bottom of the laser face. So we read laser velocity level until we become submerged. Once we become submerged, our continuous wave sensor takes over. We read a level and velocity using that sensor. All of our meters now that use laser have the ability to have a single output now that is related to basically your flow. So we can have what's called a conditional flow output. What that means is it will use laser flow until it becomes submerged for a analog output or a data storage point. Once it goes underwater, it will seamlessly submerge over and transition to the AV sensor. So now you have one signal regardless of which sensor you're using. This is a site where we early on we did some testing, and they went ahead and purchased one. At the front end of this peak, you'll see that's flow with the laser versus the flume. Very, very close. They matched almost identical. Once the laser went underwater, the AV sensor kicked in. The flume actually started overflowing the sidewalls a little bit. Once the water receded, you'll see the red line as the laser flow, and the brown line is the flume. It took about 5 days before the submergence of the flume decreased enough where it started reading accurately again. So they had one signature meter processing both of those, giving them good, accurate data regardless of what was happening at the plant. This is what the sensor looks like when it's mounted. It is retrofittable in the field. You can order a width or you can add it to it. It's no big deal to do that. Some of the ways that you can install this is a typical installation. There's just 2 bolts that hold the mounting bracket in place. There are alignment tabs on there that you can see, and those are designed so that you can actually, once you get it installed the first time, you can pull the laser above without going in the hole and putting it back down without going back into the manhole. This is a side view of the same thing, so 2 bolts, very easy to install. It is designed so that you can adjust the pitch and roll. You can also raise and lower the sensor. Normally you'll mount it at the crown of the pipe. So the sensor itself typically is mounted with the bottom of the laser close to the crown of the pipe. That way, if it does become submerged, your AV sensor is looking into the flow and you're going to get an accurate flow condition. Okay, let's talk about some applications where we use laser. Collection systems, we define those typically large pipes. When we first came out with laser, that's what we were thinking a real target was large pipes. Since that time, we're finding a lot more small pipe applications. So again, collection system, typically you're going to see some large pipes, billing applications. City of Atlanta, some of those big cities use a lot of these for billing. Hydraulic model calibration, that's another big one that we're seeing more and more of. Hydraulic models typically are involved with large interceptor lines, and maybe a lot of those you can't even get into the flow, let alone install a sensor down in the bottom. So you need a high accuracy, but you don't want to get into the flow. Stormwater, we're seeing more and more stormwater applications where lasers are being used. They can read extremely clean and very, very slow flow. That is one of the latest on laser things that I've learned over the last probably 6 months is how clean a water that laser will read and really how slow it will be able to process a velocity reading. Wastewater treatment plants. More and more wastewater plants are using lasers. Nobody wants to get into the influent and the effluent as well. So influent, effluent wastewater plants, grit chambers, things like that where you don't want to get into the flow. A lot of small pipes, more and more small pipe applications, and again, define those as anything less than 36 inches. We are seeing a lot of industrial dischargers wanting to use lasers. The reasons are obvious. The industry doesn't want to do anything with flow. They just want it to go away. Anytime you have a flume or you may have to clean the flume, may have to recalibrate things, a lot of times they're batch dump. You may have very frequent times where you have no flow, and then you may have times where they're pumping high velocity through there. Laser will be able to handle that. Water depth less than an inch. There's no area velocity sensor really in the world that's going to read or give you a velocity reading below 1 inch. Laser doesn't care how low that depth is. We can read down as low as even 1/10 of an inch of water depth. Personal property or private property ionized, another big one we're seeing now. People are trying to measure very minuscule amounts of flow. So if you get into something like that, even though it may seem like overkill compared to a standard area velocity sensor, if you have to measure those flows, nothing else is going to do it like the laser. We've done a lot of testing over the last year and a half, comparing laser to some standards to be able to say, here's how accurate. Everybody wants to know how accurate you are. What we have here is this is a tow tank test done with USGS HIF lab, and you'll notice that the laser in every point that we tested this was within 1% of the tow tank. So it did really, really well in the lab. We have other test results that we have from other independent labs like the Cal Poly San Luis Obispo irrigation facility and some other things. So we can certainly provide some amazing data. But all the lab data in the world is great. What you really want to know is what's it do in the field. So we ran the laser in series with a number of different types of technologies. This is a multipath transit time meter. What this has are multiple sensors on a ring that basically transmit across and talk to each other. These are known to be very accurate technologies. This was a test done in Japan comparing to a transit time meter. The top pane is flow rate, red is the laser, blue is the transit time meter. The bottom pane in green is the level. So it didn't matter if the level was 5 inches or 35 inches, they tracked well within 2% of each other. Okay, so that was transit time. We talked about acoustic Doppler or range-gated Doppler earlier, and we've done a lot of testing on this as well. This is the AccuPulse versus the LaserFlow. This was done with City of Omaha, and you can see the top pane, blue is the AccuPulse, red is the laser, is level velocity flow rate. The bottom pane, again, is what you're really looking for. We were well within 1% of the AccuPulse. So it did very, very well. If the hydraulic conditions are uniform, they match very closely. This is another test we did. If you look at this data, we were within 2% of the ADFM. Again, different actual pipe sizes, so there's a little bit of difference in the hydraulics, different flow patterns, a little bit of difference in the velocity as well as level, but the flow output was identical. This is another test where we compared to the ADFM, large pipe, 96-inch channels going to a wastewater plant. Top pane is level, second one velocity and flow. Interesting thing is it looks like the flow dropped out or the velocity dropped out. When we actually got the data from the ADFM and compared them, what we found out was this customer will periodically shut gates in order to flush flow through one channel in an attempt to keep the contact ADFM sensor clean. So they will shut the gate, run all the flow through one channel, they shut the gate the next day, and then again, finally they open it to the one where the laser and the ADFM were. So very, very impressive looking data, very, very accurate. Large pipe installation. This is another one where we have a lot of people trying to measure, 12-foot pipes. Well, the laser does have a 10-foot limitation currently. In this case, what the customer did was went ahead and mounted it at the top of the pipe, and instead of on the side or the crown, they mounted it at the top, and it will bring it down low enough where it's in the range of the laser itself. Okay, so we've tested in applications where we've compared to flumes. More and more people are questioning the accuracy of the flumes. And I will tell you right now that the more I work with the laser, the more I'm confident in the next year to two, people will be using the laser to verify their flumes are reading accurately. A lot of things happen with flumes. The approach velocity is too high or too low. The size of the flume is wrong. Other things can make a flume not necessarily the most accurate device. In this case, they had a signature meter using an ultrasonic to measure the level of flow in the flume, and they use the laser upstream. When it submerges, then they automatically switch to the laser. This is the flow data between the flume and a flume and the laser, track very, very close. We all, I think, agree that flumes can be within about 5%. In this case, they track very, very close. Irrigation channels or canals. We're seeing more and more irrigation canals where they're trying to measure, without getting into that. In this case, this was a site in Colorado. They put a laser in there. The flow is uniform. So if the flow is uniform, you really can get by with a single laser. You don't need to have multiple lasers. So in this case, it worked very well for them. Flexibility. Okay, so some of the things we do is signature, again, is our smart device. This signature flow meter will allow you to connect multiple sensors, up to 9 technically. In the case of laser, we'd probably hook 2, maybe 3, but normally no more than about 2 lasers on one. But it gives you a lot of capabilities. We can take in other technologies that have Modbus output, analog outputs, and so on. But the communication side of the signature is impressive. It can transmit data using cellular modem. We can also allow you to download using a USB or a thumb drive. You can use internet, again, to call up the site, analog outputs. We have alarming capabilities and so on. So very impressive. That's the signature. This application is a large rectangular channel. This was actually in this is a drinking water facility in Kansas, and they knew their flows were not very uniform. It's about 20 foot wide. So they went ahead and they installed 2 lasers. So they have 2 lasers on this channel, both kind of splitting it in half. We set the flow conversion up so we take one sensor has 10 foot, the other one has the other 10 foot. Both of those are processed in the signature and give you one continuous output for both of those. So you can average those, add them together, whatever you want to do with it. So very powerful tool in these types of applications. Okay, low level, high velocity, more and more of these types of applications. And these things, it's very, very difficult, if not impossible, to install a pipe or banded sensor, if you will, in this type of application. Currently, our spec is a 1/2 inch depth for velocity, although we will read, in the case of the laser, as far down as it can read level. So it's going to read down. In a lot of cases, I have them below, even 1/10 of an inch of level. Our current spec is 15 foot per second for your maximum velocity. The way they did this in this particular location, this is actually Duluth, Minnesota, very, very high velocity, low level, almost impossible to read. They went ahead, we put a laser in there. The laser doesn't care if it's pointed upstream, downstream. It can point, again, mount on the front wall, back wall. So very flexible as far as installing. Once you put this in, you know the XY axis, you know if it's installed correctly. There's also a bubble level in the back. So very, very easy to install for the most part, much, much easier than installing something in the pipe. This is some data from a site in Colorado. What's interesting about this is the level in this pipe is about 21 inches, and the velocity is screaming, 11.26 feet per second. This is a very difficult, if not impossible, site to measure without using laser. We do have sites actually in Canada where the velocity is even higher than that. This is a contact sensor right now. You can see the hydraulics look good coming in, but once they hit that pipe joint, you get a lot of disruption, which is going to cause you errors in level, velocity, cables coming loose, you're catching debris, all kinds of nasty stuff going on in that line. This was a really nice, neat picture I saw from a customer in Germany, but they were showing the effects of a high velocity application in a standard AV sensor. In this case, it was a 2150. So again, if you have high velocity, 2150 or 350 is going to do a good job of giving you what it thinks is going on, but you have to be aware that you may have some inaccuracies in some of your readings. This is a temporary mount. This is a hydraulic mount that we use. If you want it to go temporary, you don't want to drill any holes, you can just crank that out. The sensor mount is at the bottom there. This is one where they used actually competitor's mounting device, but what's impressive about this is the slow velocity that we're able to read with the laser. You can see the laser beam on the water itself. Our spec is a 1/2 foot per second, which is where the dashed line is. In this case, we were reading down to 0.39 feet per second velocity, very, very slow. Stormwater. This is a site out on the East Coast. The customer was struggling to try to read this. This is stormwater. The water is crystal clear, and it is barely moving. There is very low velocity, very little particles in the water, and very low level. We put the laser in. You can see the beam on the water right there. This is actually a 72-inch pipe. And what you'll see in this case is that particular point right there, my reading is 0.76 inches at 0.26 feet per second. So just a crawl of velocity and below 6 gallons a minute. Amazing what the laser is able to read. Here's another one, billing application. very small pipe. We don't care if it's 6-inch, 4-inch, we just need to see water. And again, in this particular application, you can see the laser hitting the flow, but there's not much water going through this. So may seem like sometimes overkill, but if you have an industrial customer that wants to measure flow, doesn't want to mess with it, just put it in and be done with it, the laser is a great solution for that. This is some of the data from that site. The level in that dashed line is below 1 inch. Velocity is anywhere from 2 to 6 feet per second, which is incredible. In this case, when I looked at the data, I wasn't sure how accurate it was. My Doppler power value was greater than 1,000, 2912. I know that with confidence that reading it took right there is accurate. And the flow rate, amazingly, was less than 1 gallon per minute. Unbelievable that it's able to read that. Okay, another application challenge, drop pipe. This is a customer wanting to measure flow in this pipe. So as you probably recall from my training just a few minutes ago, your level normally would be read below the laser, and it would try to read velocity below the pipe. That wasn't going to work so well. So engineering came up with a solution where we actually can remove that sensor. You order it that way, and we put the ultrasonic on a horizontal mount that now will read in the pipe, reading the level and velocity in the same location. That's going to do a couple things. It's going to allow you to read those locations, but it's also going to improve your performance and your accuracy overall. This is a site that's a combined sewer line. You'll notice the water is kind of flowing out and dropping a little bit. In the first laser, it would have tried to read below it. Not working with a lot of water there would have had some problems. We use the remote ultrasonic, and now it's able to see the velocity in the same location. This is a big pipe. This, you'll notice, is the water kind of that free falls out of that, but then it comes into a big irregular channel. So we got a very undefined location. So what they do is they went in, they used the remote ultrasonic, and it's mounted up in the pipe, and now they're reading level and velocity in that round pipe where the hydraulics are much, much better. If you have a condition looks something like this, where they have a grouted pipe, maybe it's low flow, the laser wouldn't work so well. So basically they had a 3-inch change between what was coming into the pipe and the invert. They also had some standing waves, they had some hydraulic issues and so on. So the laser has the ability to what's called adaptive focus. It's able to, it knows where it would want to normally look for the flow, but it will scan 3 inches above that point all the way through until it finds its strongest signal or the best signal. So it has a lot of intelligence if you run into cases where you're struggling to get a good reading. This is another application where we had a rotating bar screen, influent of wastewater plants. Like I said earlier, we're seeing more and more applications. People want to do non-contact coming into the plant. This particular one, 72-inch pipe, level change is 3 inches in 1 minute. So lots going on, very short amount of time. They verified accuracy using the old bucket stopwatch test. They drained a clarifier. They timed how long it took to fill it. They repeated that test 3 times, and every time it was within 2%. They also compared to the influent mag meters, and they were within 2% of that as well. So very impressive test. The level right here you can see in top is level is changing 3 inches in 1 minute. So a lot's happening, again, in a very short amount of time. The velocity you can see is going up and down as well, and the flow rate. We also had some tests at a pump station application. This was in Wisconsin. The customer put it on a constant speed pump station where it pumps on, pumps off. The interesting thing is the bottom pane is the level. It goes from 0 to about 12 inches with its snap of a finger. Velocity 0 to 6.5, 7 feet per second. But what's so impressive is the top pane, which is the flow rate. That's using flow rate comparing the mag meter. In blue there was 9.2 million gallons. LaserFlow was 9.3. So just amazing on how close those two followed each other. Okay, so let's talk about advantages, disadvantages. Laser is non-contact. Nobody does what the laser does. 5,000 velocity readings in 2 seconds is just incredible. The multi-point velocity method is the other thing where people that have used other technologies such as surface radar really, really love this capability of the laser. It will tell you exactly what's going on in those channels. We don't care if it's a large pipe or small pipe. It's always been taboo in the past to say 1 meter works in every application, and that still is true to a point. I can tell you the laser is the most versatile, one-size-fits-all technology that I've ever seen in the 30 years I've been doing this. We spec 4% accuracy for non-contact, so it's the highest accurate spec non-contact available on the market. We do have tests that far exceed or even better than 4%, but that is our spec. We don't care if it's a ½ inch deep or 120 inches. We will adapt to those conditions, so we do not have a decrease in the accuracy. The laser will read the slowest velocity of anything I know of. Even though we spec a ½ foot per second, there are applications where we will read far below it to the tune of less than 0.2 foot per second velocity. Portable permanent, again, don't care which one you want to use, uses a non-drifting ultrasonic. So really, when you put a laser in, you're done. You put it in, you set the level, make sure you're getting good Doppler readings, signal looks good, and you can monitor that remotely. So for that reason, you never have to really get back into it. It's going to cost a little bit more than a continuous wave sensor, but it's going to be less than the pulse Doppler. So if you don't have a regular velocity profile conditions, you may want to consider using the laser. It takes a little bit more power, so DC applications, you may want to use a deep cycle battery. May not work in some foam or steam applications, high fog, anywhere where you think you would have problems with an ultrasonic, you might want to consider that as a good guideline. This is a couple stormwater shots. This is a signature with a sampler in a stormwater box in Florida. This is the flow between those two, and you can see that the water is very, very clean. Stormwater, so this is another very colorful picture, but this is one in Los Angeles where they did not want to have anything exposed for obvious reasons. They would not only get painted, but probably be stolen. So they wanted to put a non-contact up into those rectangular channels. And then this is another one where we had a stormwater application. In this case, the customer just used C-clamps and clamped the bracket right to the pipe. The picture on the right is looking from in the pipe out, so it doesn't always have to be in the crown, but obviously you want to make sure it doesn't become submerged if you can, just so it doesn't tear the sensor off. And again, very easy to install that. There's a stormwater box there with a rain gauge. They had a signature meter, sampler, a solar panel, and again the laser. Okay, so when you look at your equipment options, you have to determine, do you have AC/DC power? If it's going to be permanent, you probably would want to go signature. If it's going to be a portable, you can use a signature portable unit. But if it's going to be in a manhole, you might want to consider using the 2160, which again is a submersible box that is on the upper right. Flexibility, we talked about that. Laser gives you incredible flexibility. Both designs can be remotely communicated with using cellular communications, whether it's signature or a 2160. They get up, they take readings, they're able to transmit the data to a central database. The way we do it is a little different than probably some of the other ones out there. We will typically allow you, we do allow you to go ahead and own FlowLink Pro, so you can buy the software. You host your own data, which means you spend the money up front, which is not that much. You put it on a SQL or Oracle database, and then the meters in the field transmit to your database. You have full control over it. You own your own data. We don't hold you hostage for a 30-day fee like some other people do. Data goes into your database internally. Engineering people that have FlowLink on their computers can just access the FlowLink Pro database at the same time. Remotely, you can use VPN to log in and see what's going on. And recently, you'll be able to use, or now you'll be able to use, again, remote communications to either pull up data on the internet, which is called FlowLink Global, or you can, call into the site or whatever. So very, very powerful on what you're able to do with the communications. This is kind of an example of some creativity. This was Pueblo, Colorado. They had the manhole lid actually machined this way, which I thought was very, very neat. So they recessed that antenna so now a snowplow can go over it without damaging anything. One of the older style whip antennas. We have a lot of people that we use the magnetic whip antenna, which comes standard with it. I'll show you what that one looks like. It's a little different than this one. But if you have a good cellular tower close and you're getting good signal, a lot of times that will work. You don't even have to have the antenna extend or out of the manhole. This is one where they do have a manhole external. That's known as a manhole antenna design. This is a blade antenna, which is a very neat thing. This is just either epoxied right to the lid or it has adhesive that glues right on top of it. This is one of the magnetic antennas that comes standard with the 2103 CI or 2105 CI, and it's a dual band antenna. In this case, City of Omaha just glued it or just stuck it right to the top. Milwaukee used a blade antenna here years ago testing, and they just epoxied that whole thing right to the lid of the manhole. Okay, so kind of wrapping up here a little bit. Once you get that data, one of the nice things about it, obviously, is being able to pull it up on the internet. This is known as FlowLink Global. FlowLink Global allows you to log in, so you have your own username, password. You go to the internet, anything that has internet, your cell phone, your whatever, can log into that. Once you log in, a dashboard view will pop up. What this does for you, it gives you a real quick glance at the status of your manhole or your monitoring project. So green means good, all conditions are normal. Yellow means I did not communicate in the time I thought it was going to push data. So not a hard foul, but it says, hey, I had a little bit of problem getting data to you at some time. Red means I have a hard failure. That can be anything any of our meters store. Level, high level, low batteries, bad signal on a 2150, bad Doppler power on a laser, high temperature, any of those things you can alarm off. So you can have the meter in the field sending you an alarm telling you you have a condition, you get a text message, you pull up your cell phone, you go, what's going on? And you can easily look at FlowLink Global and assess the situation right there on the site. You can also single click with FlowLink Global and get a graph. So now you can see not only level, velocity, flow, you can click on anything the meter stores. So I can look at input voltage, I can look at XY axis to see if my sensor may be shifted. This all uses GIS mapping. So now you can put in the coordinates and you can pull up a GIS map if you'd rather look at that view, which will tell you exactly what's going on at those sites with just a quick glance. So flow service companies out there find this very useful because you can do a study for City of Austin, for example, and then they can see only their data. They don't get to see everybody else's, but you can pull up a quick graph and see what's going on at their locations. Okay, so in summary, Teledyne Isco really has, I think, a solution for almost any flow application you can run into. LaserFlow is the most versatile and advanced technology I'm aware of, and I become more and more impressed every day, and I look at data from this thing all the time, and it is absolutely mind-boggling what it's able to do. It can read the slowest velocity of any technology I'm aware of. So we can read down, again, far below even our spec in certain applications, not every one, but most applications it'll read down in the 0.1 to 0.2 foot per second range. Again, our spec's 0.5. It can read dirty or clean. I get asked this question a lot. How dirty can it read? We were reading at the influent of plants. We have them in wastewater plants. Worst case, a laser would read the surface if it couldn't get in there. But you will know immediately when you set it up how well it's able to penetrate that flow. It can also read, again, extremely clean water. Because its signal is so clean, we just don't have a lot of noise. It doesn't take very much for the laser to be able to pick up a reading. And for those reasons, it is working in applications where people have never been able to measure flow. So just amazing what it's able to do. Now that you have this wonderful technology, being able to pull it up on the internet is certainly a very valuable tool. And that is, again, FlowLink Global. So at this point, I'm going to go ahead and turn it over to questions. My email address is right there. It's rick.dey@teledyne.com. Feel free to send me an email if you have any questions. I know we had a lot of people that attended WEFTEC this year that we invited on this. So at WEFTEC, I'm sure we talked and showed you what the meter's capable of doing. I thought this would be a good time to kind of give you a little more detail of really how all that technology works. So at this point, again, I want to thank everybody for attending. We're going to go ahead and open it up for questions.
Rick, I've got a quick one for you right here. What is the maximum cable length for the LaserFlow sensor between the sensor and any other monitoring device?
Okay, good question. The laser currently is 180 feet maximum length from either the signature or a 2160. If you want to run it further than that, we can do that, but what we would do is either want to power the laser locally because you have a line loss in your voltage, or you can just use an extra pair of wires and you would parallel your positive and negative, so now you basically double your current capabilities. Your voltage, your line loss is much lower, and then we can go a lot longer distance than that. The gauge of wire will depend on the distance, but digitally it can go much further to the tune of almost 1,000 feet. But we need to know. Get a hold of us if you have any questions on that, so that we can go through and review your application, make sure we give you the right right solution for that.
Okay, Rick, another question that we had pop up here is in regards to the submerged application that you talked about. Is there any maintenance that you need to do after you know your sensor has been submerged?
That's a good question. The laser itself, as I mentioned, reads the level and the velocity using laser. Once it becomes submerged, automatically switches to the area velocity, level, and velocity. When that water level recedes, the laser ultrasonic is going to keep firing away trying to get a reading, which will also give you a ultrasonic signal strength. So if you have debris on the laser, the only time I've ever seen a problem is if there was like a towel or a big rag hanging off the nose of the laser itself. Otherwise, the ultrasonic signal will tell you how well that level is reading, and then the other one will be your Doppler power. So you'll be able to see how well the laser is getting a signal back. So you have Doppler power, you have the ultrasonic signal, but we also have another thing in there called sense voltage. What that is, Bill, is the ability for the laser to determine any backscatter into the laser itself. So if water were to ever get up in there, and we designed it so the water will not get up into that window, but if it ever did, what you would see is your sense voltage value would increase to over 100 millivolts, which tells it I have fogging or something on the window, and then it will turn on a small little window heater and just warm the glass, and that will go away. So you have your XY axis that tells you the position of the sensor. You have ultrasonic signal tell you how good your level is. You have Doppler power to tell you how good your laser is. So to answer your question, long way, we have tools that will tell you you need to go there or you don't. But you'll know before you ever dive that manhole. Okay, I had a question here, Bill. We've been asked how a standard area velocity reads below 1 inch. What it does as a default is it uses 0 to 1 foot per second from 0 to 1 inch. So if I put a 2150 sensor or a 350 sensor in a manhole and I'm working with a trickle of flow, it doesn't know what the velocity is. So it's going to basically try to guess or give you its best guess. Once that water level goes above 1 inch, turns on the velocity sensor, starts getting real velocity readings. So let's say it's at 2 foot per second below 1 inch. Once it hits 1 inch, it says on 1.9876 down to 0. That is a good way to do. I mean, it does a good job once it gets to that point. The challenge, and some people will say, well, can't I dam up the flow behind that sensor to build it up? Well, you can. That'll get it above 1 inch. The problem is, once you pull that dam out, now your flow, your velocity curve that you just developed is really inaccurate because it has different hydraulic conditions. So if you need to measure flow in those types of applications, the laser is going to be by far the best way of doing it without damming up flow and causing you some problems.
Okay, I had a question come in, Rick, about the accuracy of the ultrasonic sensor on the LaserFlow. And what the question is whether or not that accuracy statement of 4% at full span, is that full span or is that full reading?
That's a really good question. I'm not sure I have an answer for that. If we have an email address, we could certainly send that to. I don't know if that's. I think it's full scale, but I'm not, or I don't know.
Okay.
Apologize for that. Here's one, battery life. How long will a laser last on a set of alkaline lantern batteries? As a standard, at 15-minute reading, single point, and if I don't have communications on it, you'll get about 12 weeks with one set of alkaline lantern batteries. If you do have a cell modem on it and you're pushing data once a day, 15-minute readings, you'll get about 7 weeks. It should be noted that again, you could stack multiple battery modules, or you can use deep cycle battery to power it. We do have a lot of people now that are using deep cycle batteries because they know they don't have to get in there and do anything with the laser. They don't have to get in there and do anything. Why go out and do anything to them? So we have some people that will either use deep cycle batteries in the manhole. They'll change those about every 4 to 5 months, depending on how they're running the laser. In some cases, like in Arkansas, they're running these things on solar power with deep cycle batteries, and they don't ever have to go really do anything to those meters. So need to kind of look at what your situation is, how long are you going to run these things, and so on.
Now, Rick, in the past, you've told me that a typical LaserFlow application just requires a single point measurement. But being the expert, what do you look for in stream conditions that make you think we need multiple point measurement or adaptive focus or some of those other extra features?
Okay. When we do a laser install startup, first thing we do is we turn on a single top middle point. That's its best chance of getting a velocity. It's the strongest signal. If I get a good Doppler power value, and again, minimum is 1,000. Normally, we're seeing 10,000 or higher. If I get a good Doppler power value, that means it likes what it saw at that point. I will then go ahead and turn on like all 15 points. If my flow is relatively uniform, and I know that's a hard thing to define, but if it looks fairly uniform, like I showed you in that grid up there, it's totally your choice. You can either turn on all 15, depending on if you have power. If you don't have power, that's really what's going to dictate how many points you want to select. We did a test in Wisconsin one time with some guys from Madison. The flow was coming into the manhole at one spot, and then there was a 90-degree pipe feeding in, and so they had some really bizarre hydraulics. Water was literally going the other direction. So we turned the laser on. It was seeing a half foot per second in one spot, and then on the other side of the pipe, it was about 1.5 feet. First thing is that's not a great location to measure flow, so I would recommend finding a different location. But if you can't do that, then you want to go ahead and probably turn on at least 3 points and let it average all those. That's going to probably be your best method of doing that. The laser does have a couple of advanced features I really didn't go into in great detail, but one of them is called peak detect. Peak detect means the laser will scan left to right, look for the highest velocity, lock in on that, and then it will use that side of the pipe to calculate the speed of the water. It also has what's called adaptive focus. Adaptive, as I explained earlier, that is kind of a last resort. If I can't get the laser to get a reading because my water is dropping into the manhole, then adaptive focus is certainly one of those tools that you can turn on that will give you your best chance of getting a reading. But that's more of a last resort method as well.